In this video, I'm going to show you how to find the area of a general triangle. So say we've got this triangle, and we know two sides, A and B, and we've got an angle between them that is also known. There's a general formula for the area of such a triangle, and it goes like this. The area is equal to 1/2 times A times B times the sine of the angle between them, theta. So this here is the formula that we're going to be using to compute the area of some triangles in this lesson. Alright, so let's move on to some exercises. Find the area of each triangle below, starting with this one here. We've got two sides, 5 and 8, and an angle between them, which is 42 degrees. So we can just go ahead and apply our formula. The area is equal to 1/2 times A times B, so really just times the product of the two sides that are surrounding the angle. So times 5 and times 8, and then times the sine of that angle, 42 degrees. And the result here, if you punch this into the calculator, you should get 13.38, rounded to 2 decimal places. So there we go. There is the area of the triangle. Alright, on to the next example. This triangle has two sides, 10 and 15. We don't know the angle between them, but we do know the other two angles, 40 degrees and 30 degrees. So how are we going to find the area of this triangle? Our formula here only works when we know two sides and the angle between them. And we know these two sides, but we don't know the angle between them, so that's an issue. But hey, we should be able to resolve that issue, because we're only missing one angle of the triangle. We know the other two angles, and we know that the sum of the angles in a triangle add to 180 degrees. So if we label this angle as theta, then we can write down an equation, theta plus 40 degrees plus 30 degrees equals 180 degrees. And we can go ahead and solve that equation to figure out what theta is. So this becomes theta plus 70 degrees is equal to 180 degrees. So subtract 70 from both sides, get theta is equal to 110 degrees. So theta equals 110 degrees, and we can say that A equals 10, B equals 15, and now we can apply our formula. So area is 1/2 times A times B, so times 10 times 15, then times the sine of that angle, 110 degrees. And the result there, if you punch that into the calculator, round to 2 decimal places, you get approximately 70.48. So there we go. There is the area of the triangle. Next up, we're given that triangle XYZ has area 40, as well as XY equals 14 and measure of angle X equals 50 degrees. And we want to find the length of side XZ. So here's our triangle. Let's first start by labeling the given information. So we know that the area is 40. And what else do we know? We also know that XY equals 14. So let's label that. That's 14 right here, XY. And measure of angle X equals 50 degrees. So this right here, 50 degrees. And now we want to find the length of side XZ. So that's our variable. Why don't we call that A? That's what we want to solve for. So what do we know that relates all of this information, A, 14, 50 degrees, to the area, which we know is 40 degrees? Well, there's just the area formula for a general triangle, which we can use whenever we've got two sides of the triangle and an angle between them. So according to the area formula for a general triangle, the area is equal to 1/2 times the product of those two sides, so 1/2 times A, the other side is 14, so times 14, and then times sine of the angle between them, which is 50 degrees. So now we can just go ahead and solve this equation here. Let's just simplify it first. So 40 is equal to 1/2 times 14 is 7, and then we've got our A, and then we've got our sine of 50 degrees. So to get A alone, we can just divide by 7 sine of 50 degrees. Do that to both sides. And then this 7's will cancel out, sine 50 degrees will cancel out, and we'll just have that 40 over 7 sine of 50 degrees equals A. And if we punch that into our calculator, we find that A is approximately equal to 7.46. And A was just the variable that we assigned to be the length of side xz, so we have that xz, that length, is approximately equal to 7.46. So there we go. We've got the length of side xz. Lastly, why does this area formula even work? Here we're going to derive the formula that area equals a half AB sine theta. Now the way to start this off is to draw an altitude of the triangle, which forms the height if B is the base. So just take a segment, drop down a segment from that top vertex there, drop it down to the base B so that it is perpendicular. So let's draw that in. That's perpendicular, that forms a right angle. Both angles here are right angle. And why don't we just label that as h for height, because that's really just the height of the triangle. Now we know, of course, that the area of a triangle is equal to 1/2 times the base, which is b here, and then times the height. Now what we're going to do is we're going to write the height in terms of the other variables a and theta. So just look in this triangle here, this right triangle. We can use trig functions here. What trig function relates h to a for this angle? In other words, what trig function relates the opposite side to the hypotenuse? Well, that's just sine. So we can write down that sine of theta is equal to opposite over hypotenuse. So h is the opposite, and then over hypotenuse is a. So solving that equation for h, we can just multiply both sides by a to get h equals a sine theta. And then we can just go ahead and plug that into our area formula. So area is equal to 1/2 times b, the base, times the height. But now the height, we know that the height is a sine theta. So let's go ahead and plug that in. So times a sine theta. And this is pretty much it. The only difference is that b and a are flipped around in the other formula, and we can just flip them around because multiplication is commutative. So let's just write that finishing touch. Area is equal to 1/2 a b sine theta. So there we go. We've got it. There's our formula. So now we know how to find the area of a general triangle using our nice area formula, and we also know why that area formula works. And this will be very helpful to us in the future as we try to find areas of weirdly shaped triangles, and we try to derive area formulas for other shapes.